Hello everybody. Today we are going to discuss the next point called as monosubstituted cycloalkanes. That is monosubstituted cyclohexanes. In this cyclohexanes we have the example of a bromocyclohexane. In last lecture we have studied about the cyclohexanone. So let us start here. First of all, I can write here. I can draw the diagrammatic representation here like this. This is okay. A cyclohexane ring here. This is axial, this is equatorial, this is axial, equatorial. Okay, this is equatorial, this is axial. This on this, here this, on this. Okay, here bromocyclohexane, that is one of the hydrogen is replaced by a bromine atom. Here He, He, Ha, He, Ha. Here He, Ha. Here Ha, He. Here now here on He, Ha. Now it converts into a flexible boat like this here. This is of this C, of this, okay. In between this we have to draw this carbon atoms are C, here C, C, here also C, here also a C, C, C. Now here C, here also a C. What are the representations are here? This, like this. In this way you can draw also here in your notebook also for the simplicity. Ha, He here, then H here also. This is transferred to on here, that is therefore we can write here as this is from bromo, and therefore here we can write it as a Br. Okay, Ha. Here on equatorial position He, Ha, He, here He, here He. Here the distance between the third and this bromine atom is equal to the 2.7 angstrom. This is a 1, this is the second, third, here fourth, and here 5. These are the hydrogen atoms. Here also this is of this H. This is considered as a Ha, He here, He, H. Here form for which carbon atom, that is F1, that is equal to here we can write it as a bromo here. Okay, here He, Ha, He, Ha, He here. Okay, then He, Ha. Okay, now this is of 1, here also 1, 2, 3, 4, 5, and here also a 6 number. Okay, now this is the chair form of bromocyclohexane. This is the flexible boat format. Flexible boat. Okay, and these are the chair forms. This is of a axial form. Okay, This is of a equatorial form. Equatorial form. Okay. Now, here on this, what is the explanation of on this? That is the distance between the bromine atom which is attached to a carbon atoms with a carbon number 3 and carbon number 5 of whatever may be the hydrogen atoms are attached as the same position. The bromine atom is replaced by from a hydrogen atom. That means what? That is this hydrogen, this bromine and this hydrogens, all three are lie in a one plane. Due to this one plane, there is a introduction of this develops a 1,3 diaxial repulsion interaction. A repulsion interaction here. Okay. Due to what? That is, these R comes to here. Therefore, they produce a internal steric strain. Therefore, there is a 1,3 diaxial repulsion interaction which causes the internal strain, and thus the molecule becomes of a chair form of a bromocyclohexane becomes a strained one. Now, in order to occupy this strained molecule of a chair form of a bromocyclohexane acquires some extra energy. Which this extra energy? That is 2.07 kilojoule per mole than the equatorial form to reduce increase the strain. Therefore, what happens? Whatever may be in the chair form of bromocyclohexane, here bromine atom acquires the axial position. It do not fix into that position. It starts to rotate into its equatorial position, thereby minimizing this 1,3 diaxial repulsive interactions, which causes what? That is the reduction of a strain, and thus the equatorial form of this bromocyclohexane becomes a more strainless molecules, and it has a less energy, and as it possesses the less energy, therefore the equatorial form of a bromocyclohexane becomes a stable one in comparison with a chair. But a chair form is a strained one, therefore it acquires some extra energy, that is 2.07 kilojoule per mole of a energy. But what happens in the normal room temperature? At normal room temperature, this chair form of bromocyclohexane and equatorial form of a bromocyclohexane interconverts to each other via flexible bond conformations. Therefore, these two conformations cannot be separated from each other, and the experimental discussion shows that about 95% of which, that is the chair form of a equatorial position of a bromocyclohexane exists, with a only 5% is of a axial form exists. As there is very small difference in potential energy by barrier, that is 2.07 kilojoule per mole exists, therefore it is possible to reduce all the strains with a average energy in between 63.4 to 84.1 kilojoule per mole, which the energy is very less. That is between these values, that is average potential energy value for this bromocyclohexane, between this and in between this, whatever may be the strain or energy of a particular chair form is very less. Therefore, the most stable equatorial form of a bromocyclohexane exists one. There is a dynamic equilibrium between, this is the equilibrium sign, equilibrium between the chair form of bromocyclohexane and equatorial form of a bromocyclohexane via flexible bond formation. Now we can have to draw here the potential energy level diagrams here in terms of a graphical point. Here the graphical point here as like this. Okay, now here potential energy. Okay, this is the graphical format of this. Okay, like this. Now this is the chair form, this is the board form. Okay, now this is the flexible form TS1, transition state 1, transition state is a 2. Okay, and in between this difference, that is equal to a 2.07 kilojoule per mole. At normal room temperature, what happens here? Dynamic equilibrium between the chair form of bromocyclohexane and the board form of a bromocyclohexane. Here, chair form of these two cyclohexanes via a flexible board here. Also, one more point is that should be added to here. That is, here due to the difference, due to less difference 2.07 kilojoule per mole here, that is here 1,3 diaxial interactions becomes less in a equatorial form of bromocyclohexane. Okay, a bromocyclohexane. Thus we have explained here, that is the potential energy diagram with a compound, that is monosubstituted form, that is equal to a bromocyclohexane. Now next point is about that is the methyl cyclohexane. Methyl cyclohexane. Okay, I can draw here the diagram. See here, what is the diagrammatic representation of here? It is like this. Of this here, that is C methyl cyclohexane here. Okay, okay, now here in front of this hydrogen atoms we can show here as this is the solid bond, this is of a which bond, that is base shaped dash bond here, and this is a dotted bond here, H. Okay, now this is the equatorial hydrogen, equatorial, axial here, equatorial. In this fashion we can write here as, that is equatorial, axial, here also a equatorial, axial, here also, okay, equatorial, axial. Now this is 1, 2, 3, 4, 5 and 6 here. Okay, this is the methyl group here substituted at this position. Okay, now first line is here the format. Here these formats are exist in between the chair form also. Here on this C, H. Now here also this type of H here. Okay, and this type of this also a H. Okay, now what about here? Now here on this here, this is the equatorial hydrogen, this is also equatorial, this is axial hydrogen, this is equatorial, this is equatorial, this is axial. Now this is axial, this is axial, equatorial, this is of a equatorial, this is of a also equatorial axial. Okay, now this is 1, 2, 3, 4, 5 and here 6. Okay, now here as far as here this is this hydrogen atom and this is also a this CH3 group. Okay, now here the case is different one, that is a methyl cyclohexane. Here we can write here as in simpler form of methyl, here chair form of methyl cyclohexane. Here at normal room temperature, these two conformers of a cyclohexane with a methyl are in a sense of a dynamic equilibrium. Dynamic equilibrium here. Now, as far as this methyl group is considered, here methyl group is very bulkier than the hydrogen atom. That is, CH3 group is bulkier than the hydrogen atom. Therefore, when this CH3 group is present in an axial positions, due to the 3 carbon atoms of hydrogen and 5 carbon atoms of hydrogens, these are exist in only one plane, which generates a 1,3 diaxial repulsion interactions. Which causes the steric strain in the molecule. Therefore, the chair form of this methyl cyclohexane becomes a strain rubber. In order to occupy the less energy, it can acquire the extra energy other than the equatorial form. That much energy is equal to 7.01 kilojoule per mole. Thus, the molecule becomes a less energetic, but it is a least favored configuration. Okay. Therefore, methyl group is tried to position in a equatorial position in order to minimize the 1,3 diaxial repulsion interaction, so as to minimize the steric strain, that is the internal strain in the molecule. Thereby, this configuration of a methyl cyclohexanone becomes a less strain one and it becomes the less energetic one. Thus, the equatorial form of methyl cyclohexane have the less energy. Therefore, it is a more stable configuration one here. Okay. Now we consider the potential energy level diagram here. See the diagrams here. As far as the diagrammatic representation is considered here, the diagram is that here, that is equal to this on this, here on this. This is axial form and this is of a equatorial form. This is about this energy is about the 60 to 84 kilojoule per mole. This is the flexible form. Okay, as far as the potential energy, and this difference is known as the 7.01 kilojoule per mole. Axial form of the methyl cyclohexane. Okay, thus this is the potential energy level diagram for this methyl cyclohexane. As far as the axial form of difference and equatorial form of difference, here we have represented the difference is equal to 7.01 kilojoule per mole, which becomes a very less, which is of having this, that is transition state 1, transition state 2 of this chair to transition. That is the average energy is equal to 60 to 84 kilojoule per mole. But at room temperature, both the forms of a methyl cyclohexane are interconvertible to each other. Therefore, these methyl cyclohexane chair and board forms cannot be isolated. One that can be interchangeable or interconvertible to each other. About 95% of a equatorial form is stable, and about 5% of this axial form of methyl cyclohexane exists. Okay, thank you. Thus, about 95% of the equatorial form of methyl cyclohexane will be stable, and 5% of axial form of methyl cyclohexane is stable one. Therefore, most stable form of methyl cyclohexane is which? That is the equatorial form of methyl cyclohexane. As far as the methyl group is considered here, in comparison of hydrogen, methyl group is very bulky. Therefore, it can't fix up or it can't occupy the axial position, so as to minimize the diaxial interaction, repulsive interactions. Methyl groups tries to fix at, that is the equatorial position. Okay. Thus, in this way, I have explained you, that is the bromocyclohexane and methyl cyclohexane of conformers through a chair and board or flexible conformers. If are there any problems, you can ask me on these groups. Okay. Again, I am repeating this. That is, here one more mistake is taken by me, that is in the graphical nature, that is of these graphics. First, I am writing in case of a bromocyclohexane here. Bromocyclohexane, you have to keep the difference like this. Okay. Here, this difference is due to the axial form. By mistake, it can be here written as a board form. Simply just here, this is axial and this is a equatorial form. This is a equatorial form here. Also, see here, that is the positions are due to this are, that is first is a axial form and this is second one is a equatorial form here, and this difference in a bromocyclohexane is due to this 2.01 kilojoule per mole. That is in case of a bromocyclohexane. Here we are talking about TS1, TS2 here. Okay. Now in case of this a second point, that is of this which bromocyclohexane, methyl cyclohexane here. In case of this methyl cyclohexane also, here the also, that is equal to this. Okay, this is axial one and this is a equatorial one, and this is of a cyclohexanol is what happens here. That is again I am drawing here, that is this difference, and this difference is nothing but is which 2.8 kilojoule per mole. Here axial and here equatorial. The difference is due to here TS1, here TS2, here flexible board format. This is in the case of which, that is a methyl cyclohexane. Difference is equal to 7.06 kilojoule per mole. Here 2.8 kilojoule per mole in a cyclohexanol. And in bromocyclohexane, what is the difference? That is 2.01. Thus, by simple mistakes I have written in here instead of chair and board, but it is a axial and a equatorial forms of this respective cyclohexane. That is, this is a bromocyclohexane, bromoaxial cyclohexane, equatorial bromocyclohexane, and so on. Okay, thank you.